In the last lecture, we talked about the version of the theory of relativity that Einstein put forth in 1905. This theory, which is now known as the special theory of relativity, describes how lengths in space and durations of time are different to observers moving at different speeds in different frames of reference. And although special relativity predicts many observed phenomena correctly, this theory is also incomplete. And even Einstein himself was aware that it was incomplete from early on. For one thing, special relativity can only be applied to objects that are moving at a constant rate of speed. In this sense, special relativity is like a theory for your car that describes how it moves and behaves with its cruise control on, but that doesn't know anything about the brake pedal or the accelerator. And secondly, in the theory of gravity that existed at the time, the Newtonian theory of gravity, gravity's attraction works instantaneously, pulling bodies together across great distances in space without any time delay. But according to special relativity, nothing can move faster than the speed of light. This made it hard to reconcile special relativity with this aspect of Newtonian gravity. So in at least two different ways, Einstein's theory of special relativity left us with important and unanswered questions. Shortly after publishing his special theory of relativity, Einstein began to work toward creating an even more complete and far-reaching theory of space and time. It took him another decade, but eventually Einstein came up with an expanded and complete general form of his theory. This theory, the general theory of relativity, was not only a theory of space and time, but also provided us with a deeper and more powerful way to think about the phenomenon we call gravity. In around 1907, Einstein had his first important conceptual breakthrough that would put him on the road to general relativity. This was only a couple of years after special relativity and his other breakthrough papers from 1905. Thinking about how he might be able to incorporate acceleration and gravity into his theory, he came up with something we now call the equivalence principle. To understand this concept, imagine that you're in an impenetrable chamber. You can't hear, see, or otherwise know anything about what's going on outside of the chamber. Toward one side of the chamber, you feel a force. This force feels just like gravity does. It pulls you toward one side of the chamber, and it allows you to walk normally along what feels like the bottom of the chamber. But is this really the force of gravity? Instead, what feels like gravity to you might be the consequence of the chamber being accelerated. When you're in an elevator that's speeding up or accelerating, you feel a downward force that makes you feel slightly heavier than normal. And when the elevator is slowing down, you feel an upward force, making you slightly lighter. The fact is that the force of gravity feels exactly the same as the effects of acceleration. So to someone sealed in the chamber, there's no way to know whether the force that they're experiencing is in fact gravity, or is instead the consequence of the chamber being accelerated. This is the essence of Einstein's equivalence principle. And although we didn't know exactly where it would lead him yet, this insight made Einstein begin to speculate that acceleration and gravity might be very deeply interconnected. To better appreciate the nature of the equivalence principle, consider what we mean when we use the word mass. In Newtonian physics, there are two very different kinds of quantities that we sometimes call mass. The first of these is the kind of mass that resists acceleration. We call this inertial mass. Something with a lot of inertial mass, like a boulder, for example, requires a lot more force to move than something with much less inertial mass, like a baseball. The second kind of mass is the mass that gravity acts upon. We call this kind of mass gravitational mass. The weird and surprising thing is that the inertial mass of an object always seems to be exactly equal to its gravitational mass. As far as we know, there are no objects in our universe with more inertial mass than gravitational mass or vice versa. For some reason unknown before Einstein, the inertial mass and gravitational mass of an object were always exactly the same. But Einstein's equivalence principle provided us with an insight as to why this was the case. After all, Einstein was beginning to think that the force of gravity was really just acceleration in some sense. And if this was the case, then it might not be all that surprising that gravitational mass was really just the same thing as inertial mass. Well before Einstein constructed his theory of general relativity, he recognized a particularly important consequence of the equivalence principle. Beams of light should be subtly deflected or bent by the force of gravity. A few years later, in 1911, he published an article that pointed this out. He entitled this article "On the Influence of Gravity on the Propagation of Light." And in it, Einstein presented a calculation showing that a ray of light passing by the sun should be deflected by about 0.83 arc seconds, or about 1/4000th of a degree. A very subtle effect indeed, but one that could in principle be tested. But under normal circumstances, any light that was deflected by the sun would be lost in the much brighter sea of ordinary sunlight. In order to see or detect the deflected beam of light as it skims past the sun, the light of the sun would have to be blocked out. So in order for such a measurement to succeed, it would have to be made under the conditions of a nearly perfect solar eclipse. The next solar eclipse was predicted to take place 3 years later, in 1914. At that time, Einstein hoped that his prediction and the equivalence principle along with it would be proven correct. Einstein spent the years leading up to the scheduled eclipse considering some of the conceptual questions that were raised by the possibility of the gravitational deflection of light. In many applications, beams of light had long been used as the very definition of a straight line. If the sun's gravity could bend the trajectory of a ray of light, then at least in some sense, gravity could change the geometry of space. With this insight, Einstein began to recognize the deep connection that exists between what we call gravity and the geometry of space and time. But even Einstein was not yet in any position to really understand this connection. In order to build the theory he was beginning to imagine, Einstein would have to dig much deeper into the mathematics of geometry, deeper than any physicist had ever gone before. In high school, you probably took a geometry class, and in that class, you were almost certainly taught a system of geometry that's called Euclidean geometry. Your teacher might not have told you that they were teaching you Euclidean geometry, but they were. Until Einstein came along, physics was entirely based on Euclidean geometry. To almost everyone at the time, Euclidean geometry was seen as the only reasonable way to think about space. Euclidean geometry is named after the ancient Greek philosopher and mathematician Euclid. And everything about it can be derived from 5 basic rules, sometimes called axioms or postulates. When you hear these postulates, they seem very self-evident. For example, one of Euclid's postulates says that any 2 points in space can be connected by a straight line. And another says that all right angles are equal to each other. Pretty uncontroversial, right? But one of Euclid's postulates, his 5th postulate, turns out to be on less solid footing. This 5th postulate says for any straight line, there's exactly one straight line that is parallel to it that passes through any given point in space. Among other things, this last postulate can be used to show that 2 parallel lines will never meet or cross one another. In your high school geometry class, you were probably taught this postulate as an indisputable fact. After all, it seems so obvious, it's hard to even imagine that it might not be true. Throughout most of history, Euclid's postulates were treated as self-evident and indisputable. But in the first half of the 19th century, a few mathematicians started to think about systems of geometry that broke one or more of these postulates. In particular, a number of mathematicians had managed to develop self-consistent geometrical frameworks that do not adhere to Euclid's 5th postulate, the one about parallel lines. In these new non-Euclidean geometries, 2 parallel lines do not necessarily remain parallel. Instead, 2 straight lines that are parallel to each other at one point in space can come together or diverge from one another as you follow them along their paths. In these geometrical systems, it can be shown that the 3 angles of a triangle don't always add up to 180 degrees. They can add up to a larger or smaller number. And the ratio of a circle's circumference to its diameter doesn't have to be equal to the number pi, Within these non-Euclidean systems, much of what you learned in high school geometry turns out not to be true. But just because a mathematician can write down a weird geometrical system doesn't mean that it's real in any physical sense. Mathematics is certainly useful to physicists, but not all mathematical possibilities are realized in nature. What these 19th century mathematicians had done was to prove that logic and reason alone don't force us to accept Euclidean geometry. There are, in fact, other self-consistent possibilities. Whether or not those possibilities have anything to do with our physical world remained an open question. Intrigued by these strange new systems of geometry, a handful of mathematicians and physicists began to consider whether they might have anything to do with our physical world. But despite a few intermittent shows of interest, most physicists didn't take these exotic geometries very seriously. That is until Einstein placed them at the very heart of the general theory of relativity. By 1912 or so, Einstein had more or less all of the major conceptual pieces in place for what would ultimately become his general theory of relativity. But this doesn't mean that he had a working theory yet. He did not. There was still a long way for him to go before he or anyone else would be able to come up with a workable theory that could connect the force of what we call gravity with the geometry of space and time. To complete his theory, Einstein needed to produce an equation, or perhaps a set of equations, that could be used to relate the distribution of matter and energy with the geometry of space and time. These equations are known as the gravitational field equations, or sometimes just the field equations. With the correct gravitational field equations, one could calculate things like how objects should move through space under the influence of gravity. Without these equations, you can't do much at all with Einstein's theory. The missing equations were essential, and Einstein knew it. Einstein spent much of 1912 working with his friend and colleague Marcel Grossmann on precisely this problem. In doing so, they found themselves taking two very different approaches. At times, Einstein adopted a mostly physical strategy. In doing so, he relied primarily on his intuition for physics, something that Einstein had in spades. He thought it was important that he come up with a set of field equations that mimicked the Newtonian equations of gravity under certain circumstances, and that respected some basic and long-standing physical principles, like the laws of conservation of energy and conservation of momentum. Einstein also insisted that the equivalence principle must somehow be manifest in these equations. At other times, however, Einstein took a very different and much less physical approach. In these instances, Einstein focused instead on the formal mathematics of the problem. Just for the record, I want to say that this was no ordinary math problem. To incorporate gravity into a system of non-Euclidean geometry is an incredibly difficult task, and it involves what is known as tensor analysis. Graduate students in physics departments sometimes take a whole course on this topic, and that course is often seen as one of the most difficult. And let's keep in mind that in a course like that, the students are just trying to learn the math. Einstein was trying to invent it. In any case, neither of these two strategies worked out particularly well for Einstein. His physical strategy led to equations that had some features that he liked, but had some serious mathematical problems. In particular, these equations were not covariant, which means that they couldn't be self-consistently applied in all frames of reference. Any equations that were not covariant couldn't be the right equations, and Einstein knew it. From the more mathematical approach, Einstein came up with some very elegant and entirely covariant field equations. In fact, these equations were quite similar, but yet different from those that would ultimately appear in the final version of Einstein's theory. But at this point in time, Einstein became convinced that these equations didn't align well enough with the predictions of Newtonian gravity. If this had been true, these new field equations would lead to erroneous predictions for some well-measured things, like the orbits of planets, for example. We now know, however, that Einstein was wrong about this. This early set of field equations does in fact mimic the Newtonian predictions in the correct limit, but Einstein didn't know that at the time. Einstein also objected on the grounds that these equations don't respect the conservation of energy or momentum. For these and other reasons, Einstein jettisoned this set of field equations. Considering how close they were to the right answer, this was almost certainly a mistake. Instead, Einstein embraced the equations that came from his physical strategy, which were in fact much more problematic than the ones he had decided to throw out. So in 1913, Einstein and Grossman published a paper entitled An Outline of a Generalized Theory of Relativity and of a Theory of Gravitation. Conceptually, this paper contained all of the major elements that would later make up the general theory of relativity. But in this version, many of the details were far from correct. And importantly, this version of the theory was not covariant, and thus was not mathematically self-consistent. By calling this paper an outline, Einstein himself seems to have been acknowledging that this couldn't be the final answer. But it still represented an important landmark in the way to Einstein's ultimate theory. For decades, scientists had noticed that the orbit of the planet Mercury doesn't precisely agree with the behavior that is predicted by Newtonian gravity. It's close, but it's not in perfect agreement. More specifically, the orientation of the ellipse that makes up Mercury's orbit rotates by a small amount each year. This is called the precession of the perihelion of Mercury's orbit. And by Einstein's time, the rate of this precession had been measured to be off, or in disagreement with the Newtonian prediction, by about 43 arcseconds per century, or about 0.01 degrees per century. Some scientists had even imagined that there might be another planet somewhere nearby that was gently tugging on Mercury and slightly altering its orbit, a planet that they named Vulcan. But Vulcan, it turns out, doesn't exist. We now know that Mercury's orbit doesn't agree with the Newtonian prediction because the Newtonian prediction is slightly wrong. To make a more accurate prediction, we need Einstein's theory of general relativity. But the version of this theory that Einstein published in 1913 doesn't lead to the right answer to this question either. Instead of the correct rate of 43 arcseconds per century, this version of Einstein's theory predicted only 18. Einstein worked out this calculation himself, and he knew that it was a problem for his theory. As time went on, Einstein also became increasingly concerned that his theory wasn't covariant, and therefore wasn't internally self-consistent. In early 1914, Einstein wrote something in a letter that I think does a good job of capturing his feelings at the time. Here's what he said: "Nature shows us only the tail of the lion, but I have no doubt that the lion belongs with it, even if he cannot reveal himself all at once." Einstein was confident that there was in fact a great theory out there to be discovered, a theory that would connect the geometry of space and time with the force of gravity. But he also knew that he hadn't found that theory yet. He'd seen the lion's tail, but not yet the lion. At this point in the story, Einstein had spent 3 years searching for the correct field equations that would complete his theory of gravity, geometry, and acceleration. And now it was 1914, the year that the solar eclipse I mentioned before was predicted to take place. With this event, it was thought that one could measure the deflection of starlight around the sun with enough accuracy to test Einstein's notion of the equivalence principle and to test the basis of the general theory of relativity. With this goal in mind, a group of astronomers set out on an expedition to Crimea, where the eclipse of the sun would be total. But only a few weeks before the eclipse, the First World War broke out and the astronomers were captured by the Russian army. I guess they must have seemed like likely spies to the Russians, but in any case, the astronomers were held as prisoners for a matter of weeks, which was long enough to make it impossible for them to make any measurements of that year's solar eclipse. Einstein, of course, was very disappointed by this missed opportunity, but in reality, he had just dodged a bullet. Einstein didn't know it at the time, but the equations he was using were incorrect, leading him to predict the wrong amount of deflection by the sun. The correct amount of deflection was actually twice as large as the value that Einstein had calculated and published. If the team of astronomers had been able to carry out their measurement, they very likely would have shown that Einstein was wrong, discrediting him and all of the work that he had done up to that point. But of course, no one could have known this at the time. Einstein did know, however, that the current version of his field equations had problems. They were still not covariant, and on top of this, Einstein knew that they predicted the wrong behavior for Mercury's orbit. But despite these problems, Einstein gradually became more instead of less confident in the validity of his incorrect result. A full decade had passed since he first published his special theory of relativity, and I'm sure he must have been very frustrated and exhausted after so many years of effort. In any case, it was around this time that Einstein began to present publicly the incorrect version of his theory. In a week-long series of lectures in June of 1915, Einstein presented the incorrect version of his theory to a group of physicists and mathematicians at a university in Germany, going into considerable detail. Among those in attendance was David Hilbert, one of the world's most brilliant mathematicians and perhaps one of the greatest and most influential mathematicians of all time. Hilbert immediately took a great interest in Einstein's new theory. In hindsight, we can see that Einstein already had all of the most important physical pieces of his theory correctly in place, elements like the equivalence principle, among others. But Einstein's math was inconsistent and at times incorrect. Hilbert seems to have recognized this, and he began to work toward producing a correct and complete form of general relativity, perhaps before Einstein himself would be able to do so. With Einstein and Hilbert both working toward the same goal, the remaining months of 1915 became a race to see who would be the first to complete the greatest and most celebrated theory in the history of physics. But before Einstein would be able to make any further progress towards this goal, he would first have to recognize the fumbles and missteps that he had already made. This happened gradually, and by October, he had finally realized how serious the problems were with the current version of the theory. At long last, Einstein abandoned it completely. In its place, Einstein returned to his earlier work, focusing on the results that he had produced years earlier while pursuing the more mathematical version of his strategy. After spending weeks looking over the notebooks that he had produced in those earlier years, Einstein began to recognize some of the conceptual mistakes that he had made at the time. Apparently, there's something to be said for looking at something with fresh eyes. Einstein gradually became convinced that using this approach, it was possible to construct an entirely covariant form of the field equations, exactly the thing that his theory was missing at the time. Furthermore, he could see how those equations would incorporate the equivalence principle and how they would match the predictions of Newtonian gravity for things like planetary orbits. There was still an excruciating math problem ahead of him, but for the first time, Einstein saw the way forward to the final version of his theory. Over the entire month of November 1915, Einstein worked feverishly toward the goal of producing the final, correct, and totally covariant form of his field equations. By the middle of this month, he had gotten pretty close, but not yet to the final answer. At this point, however, he saw how it would be possible to correctly predict the details of Mercury's orbit, something that he had failed to do up until that point. Einstein also recognized by this time that his old prediction for the deflection of light had been incorrect. He now knew that it was a lucky break that the eclipse of 1914 had never been measured. During this time, however, Einstein was extremely anxious that Hilbert was going to beat him to the final answer. After spending an entire decade on this problem, the thought of Hilbert getting the credit must have been consuming for Einstein. But in mid-November, Einstein received a copy of Hilbert's paper presenting his version of the field equations. In many ways, Hilbert's results were similar to Einstein's own work. Hilbert had in fact made many of the same realizations Einstein had recently made. But neither Hilbert nor Einstein had the correct version of the equations that they were both looking for, at least not yet. Finally, on November 25th, 1915, Einstein presented the equations that are found in every textbook on relativity today. By only the thinnest of margins, Einstein had beaten Hilbert to the correct answer. This final version of the gravitational field equations is entirely covariant and completely mathematically self-consistent. They predict the orbit of Mercury and the deflection of light entirely correctly. And they suffer from no physical or mathematical problems. They describe how our universe truly is and how it truly behaves. Einstein's final equations are also mathematically elegant. And despite being unusually hard to put to use in practice, they're actually quite simple from a conceptual point of view. These equations relate a set of mathematical quantities known as tensors. Some of these tensors describe the geometry of space, while another describes how matter and other forms of energy are distributed throughout space. Technically speaking, Einstein's field equations are a set of 10 different equations. Each of these equations are related and interconnected to the others, and to find a useful solution, you generally have to solve all 10 of these equations at the same time. These equations are particularly difficult to solve because they are what mathematicians call nonlinear, which means that when you change one input, you invariably end up changing a bunch of other things at the same time. Einstein himself had to use various simplifying approximations to make the initial predictions of his theory. These days, relativists often use supercomputers to find approximate, but potentially very accurate solutions to these equations. So in 1915, Einstein completed and published his general theory of relativity. This theory is widely considered Einstein's greatest contribution to science and perhaps the greatest scientific accomplishment of the 20th century, if not of all time. Before Einstein, physicists thought of gravity simply as a force that attracts massive objects toward one another. And in a sense, this is correct. Gravity does pull us downward and toward the Earth, and gravity keeps the Earth in its orbit by pulling it toward the Sun. But this view of gravity, the Newtonian view, fails to recognize the greater significance of the phenomenon we call gravity. What Einstein had discovered is that gravity is not merely a force, but is instead the very manifestation of the shape or geometry of space and time. According to Einstein, the presence of mass and other energy changes the geometry of the surrounding space and time, curving or warping it. And this curving or warping causes objects to move through space differently than they would have otherwise. When an object moves through space far away from any massive bodies, and without being pulled or pushed by any forces, it simply moves forward in a straight line. Well, according to Einstein, when the Earth moves in its orbit around the Sun, it too is moving in a straight line. The presence of the Sun has reshaped the geometry of the solar system, bending space and transforming the Earth's trajectory. Gravity isn't a force at all, according to Einstein. It's geometry, which is a consequence of mass and energy. By explaining gravity in terms of geometry, Einstein overturned hundreds of years of established physics. Furthermore, his theory was not only profoundly creative and mathematically elegant, it is also right. By this I mean that the predictions of this theory agree extremely well with any number of observations that have been made. To date, no experiment or other test has been found to conflict with the predictions of general relativity. Maybe one day we'll find some circumstance under which Einstein's theory fails, but nothing like that has been found so far. In modern times, scientists and engineers have found ways to measure and test the effects of general relativity with incredibly high precision. For example, in order for the satellites that make up the global positioning system to determine the locations on the surface of the Earth with the 5 to 10 meter precision that is currently possible, they have to keep time with an accuracy of about 20 nanoseconds or so. But according to general relativity, time passes differently for the satellites than it does on the surface of the Earth because of the differences in the Earth's gravity and the corresponding curvature of space and time. Without taking general relativity into account, the global positioning system would only be accurate within a kilometer or so. The fact that the GPS satellites can determine my location within a distance of only a few meters is only possible because they take into account the effects of general relativity. To summarize, in this lecture we talked about Einstein's greatest achievement, the general theory of relativity. Although this is certainly an example of something that Einstein got very right, he did make a number of mistakes along the way. In the next lecture, we'll take a look into one of the most interesting predictions of this theory, something that Einstein in fact got quite wrong. The prediction that I'm talking about is the existence of the strange objects known as black holes.